Good morning, everyone. So I'm going to talk about my research. My research is in two areas. First area is data analytics, and another one is application of data analytics to bioinformatics problem. So, but here, obviously, I'm going to talk about the research in data analytics. So I'm going to talk two pieces of my recent work. The first one we call a semi-supervised classification. So now, suppose a patient, let's say, a patient undergoes a surgery and doctor remove let's say something like a tumor. Then the next step would send some samples of this tumor to a pathological lab to determine if this is a benign or a real tumor, right? So the traditional way is that doctor, gets samples, examines the tissue under the scope, microscope, to determine if it's a benign or a tumor. But now, more recently, researchers are developing this method using molecular signature, or more specifically using expression level of thousands of genes to determine if this is a real tumor. So now, if we use gene expression, we have thousands of genes. Right? We have basically we need to develop a computational algorithm we call the classify to do the job to classify this is a tumor or benign tissues. So this is a challenging problem. We have a thousand of features, and also we want to use some we call the labeled data. We know this is already a tumor or benign tissue, or we have also some unlabeled data. We don't have any label yet. We don't know it's a tumor or benign tissue. So then we developed an algorithm called the semi-supervised sparse logistic regression algorithm. We form a optimization problem. This problem object function is a non-convex, non-smooth function. But anyway, we developed an algorithm, and we apply this algorithm to several data sets, and then our algorithm performance on the top is the best performance. This result is in a paper we submitted to a journal. It's under review. And then I want to spend maybe 2 more minutes on another work called gene network inference. We know expression of a gene is one gene is regulated by other genes. For example, in the picture there, one gene in the beginning of this gene, there are 5 binding sites of other genes. When other gene binding to this binding site, so they are going to activate or suppress expression of this gene. So genes, they are intact, form extensive network. So now if we have expression level of genes, for example, this Y of thousands of genes, we want to infer the structure of this gene, this gene network. So also we want to use some information in the DNA sequence we call UQTL. So this X, so the goal here is infer the gene network structure. So now we form a mathematical model called structural equation model. So Y of gene J is regulated by other genes and also affected by we call the EQTL. So we form a structural equation model. And now this model, the unknown parameter in this model is B. This B matrix can be thousand by thousand matrix. It's a big matrix, have millions of variables there. But what we know about this matrix is this matrix is sparse, which means although we don't know which number is non-zero, but we know there's a lot of zero in this matrix. So using this property, we form what happened? I don't know what happened. Suppose there's something. But anyway, we form a optimization problem again. This optimization problem have millions of variables, and as non-smooth, non-convex, we develop an algorithm, and we estimate the gene network, and we compare the performance of this method with other state of other method. We get the best performance. So I guess that's all.